Okay, um, today I want to talk about uh, particles. Let me get a share screen going here. So with ThreeJs, we've talked about area lights and image effects and custom shaders. We'll talk about these other things as we go along. Today I want to talk about particles. But before I go into ThreeJS's particles, I want to drop back to our author's to our author's book and run through some particle stuff from there. The reason being that ThreeJS, as we know, hides a lot of stuff from us so that we don't have to deal with it. And if it's hidden, we don't understand it. And our author makes us work a lot harder. So the goal here is to make some kind of fire particle effect. We have these particles floating around doing different things. And we'll do this using particles that have textures on them. You can kind of see the particles here as they come up. They have some texture on them. This is adapted from this website. I believe Learning WebGL is broken, perhaps. The JavaScript's fairly simple. All it does is get stuff to the shaders and then simply redraw those points. We're going to draw these particles as points, and I'll come back and look at that later after we look at the shaders. First, the Vertex Shader. It's fairly simple. We have 4 attributes. We have a particle's lifetime, a lifetime. Its starting position in X and its Y speed, and a vec2, a color. We have uniforms for time. We're going to use the system clock to make things move along. We have the point size, and we have varyings for V lifetime and color that are going to be passed on from the fragment shader, from the Vertex Shader. For our clock, we're going to mod the time that is passed in with a lifetime. So each particle is going to have a clock that goes from 0 to a lifetime as the U time progresses. And we'll form this TI as 1 minus this cyclical lifetime that's going from 0 to a lifetime divided by a lifetime. So TI is going to go from 1 when the particle is first born and its V lifetime is 0 to 0 when the particle is at its full lifetime, a lifetime. So then it's 1 minus 1 and it's 0. So TI starts at 1 and then goes to 0 as the life expires. Oops. Sorry about that. So the rest of this, we're going to, in the Vertex Shader, we're going to set the particle's position. Its X position is going to be its AX position times TI. TI starts at 1, so it starts at AX position. And TI goes to 0 over time, so it moves to the center of the screen. Y is going to start off at -1 when V lifetime is 0, and it's going to go to AY speed times A lifetime as the particle ages. V lifetime maxes out at A lifetime, so it's going to go to that -1. Notice in the position here, I'm keeping the Z coordinate 0, and I'm counting it as a point. And I'll remind you also that A lifetime, A X position, and AY speed are all attributes that can be set individually for each of the different particles, each of the different particles that we're making. So the last thing we do is we're going to assign the point size to be the uniform U point size. All our particles are the same size. And I'm going to set the two varyings, V lifetime, which I used before back here, that goes from 0 to A lifetime. I'm going to replace it with 4 times Ti times 1 minus Ti, which is a parabola. This, when Ti is 0, it's just been born, V lifetime will be 0. When Ti is 1, when it's just about to die, the lifetime is also going to be 0, and it'll be parabolic in between with a maximum value of 1 at Ti equal a half. So we use V lifetime in 2 places for 2 different things. We're passing on the varying V lifetime to the fragment shader. And remember, this is a varying, so it's interpolated among all the different polygons. So in the fragment shader, we're going to assign the fragment color as a combination of a sampled texture, S texture, that is combined with that varying Vec2 color that we passed on. Here, we're sampling from the texture into text color. We're multiplying that by a Vec4 that has in slots 1 and 2, that Vec2 color has a 0 in the blue channel and a 1 in the alpha channel. But then I'm going to replace the alpha channel of my fragment color with that V lifetime. The V lifetime, as you remember here, is going from 0 to begin with to 1 at half lifetime to 0 when the particle dies. So our particle will fade in to a maximum value and then fade out. They don't pop into existence. Now, there's a little trick here regarding the sampling. We're not sampling with a UV coordinate here. We're sampling instead with the GL point coord. And GL point coord is the location within a point primitive that defines the position of the fragment relative to the side of the point. Points are little window space squares whose size depends on how many pixels we assign to it by the point size. Since these points are a single vertex, the only way to know where in that square a particular fragment is with the GL point coordinate, which goes from 0 to 1 using a left-hand origin for the point coordinates. 0, 0 is the upper left of our little point square. Here's the texture that we're going to use. It's just a smudge that's kind of black around the edge and white in the center. It's a GIF. We load it in the usual way with a load texture. We load texture, goes through the various setting of the wrapping, the min and mag filters, and binding the texture and sending it to the GPU. As we set up our some number of particles that we're going to have, we're going to assign random values to the lifetimes, random between 1 and 3, to the x positions, random between minus 0.75 and plus 0.75, random y speeds from 0 to 0.7. And you remember I said that the maximum y value of our point was y speed times lifetime, so minus 1, so 0.7 times 3 is about about 2, minus 1. So they're going to go up a certain height. And here the vec2 of colors, which we're pushing twice to get the red into the first channel and the green into the second one. The red is going to be between 0 and 1, and the green is going to be between 0 and 0.2. More red, a little bit of green. That'll be important later. Sending all these different attributes to their appropriate place in the shader. Notice here I'm not using flatten, and that's because I used arrays here with push. So these are not the author's structures, and so we don't have to flatten them. The colors, remember, is a vec2, so it's only the red and green channels of our color here. Time we get from date get time. It's got a location. We specify the point size to be, I think it's the window size divided by 5. 1/2 the window width size was set somewhere else. And the render function is very simple. We catch a copy of the time, we figure out the elapsed time, send that to the shaders, clear the buffer bit, draw the points, and request an anim frame to go around again. Notice here I'm not clearing the depth buffer. I'm only clearing the color buffer, not the depth buffer. And that's because we're blending colors here instead of overlapping them. Since we're not doing depth testing for who's in front of whom, we need to deal with how colors of overlapping pixels are blended. And here we venture into a TMO, too many option world of the blending functions. First, we need to enable blending and then specify the blend function. We're specifying the blend function to be GL source alpha and GL1. Now, the blend functions, there's the S factor, the first argument, and the D factor, the second argument. You can think of the S factor as the source and the D factor as the destination, or you can think of it as the S factor as the foreground and the D factor as the background. The pixel that's in front and the pixel that's behind, how are these two overlapping pixels going to be combined? Now, the default that we use when we don't bother with this is GL1. This corresponds to 4 ones, 1, 1, 1, 1. Here's a website. You can play with all the different blending options. Without blending, ordinary depth testing renders the polygon in front. But with blending, the two textures are combined according to the rules that we're specifying with these chosen 2 arguments of the blend function. Here are all the different options for blending. Here's that GL1, it's all ones. Here's one called GL source color, which is the red, the green, the blue, and the alpha of our source texture. And here's GL source alpha, which is one of the ones we're going to use here. It's the alpha source, alpha source, alpha source, alpha source. So the front pixel's alpha value are the 4 values of the blending function. How does it blend? Here's source alpha is alpha in each of the 4 slots. And here's GL1, which is 1 in each of the 4 slots. So for each of the 4 channels, the resulting red intensity is going to be the alpha of the source times the red of the source plus the 1 of the destination times the red intensity of the destination. These are the 4 alphas of source alpha, and these are the 4 ones of GL1. So recall in our fire, we had that varying lifetime that was the little parabola that went from 0 to 1 and then back to 0 again. And we used that for the alpha channel of our texture. So in our blending, when they start off, the alpha is 0. So 0 times red source gives me a 0. And the 1 times red destination gives me a red destination. And so the resulting color of this blending is going to be the background pixel. The front pixel is completely transparent. As we get up to TI equal 0.5, the alpha channel is now 1. So we have 1 times red source gives me a red source. 1 times red destination gives me a red destination. And we add those two together. So this resulting red intensity is the combination of the source and destination's red channels. Similarly for the other 3 channels as well. They're combined in exactly the same way. If we consider a different example, for instance, there's a 1 minus source alpha, where each of the 4 numbers is 1 minus alpha, 1 minus alpha, and so forth. Since alpha starts off 0 with our little TI thing, it's going to be initially opaque. So it'll be RS. And we have 1 minus RD, so that'll be RD. So that'll add the 2 components together. So the particle would start off with a combination of front and back. At TI equal 0.5, the alpha channel is now 1. So this now becomes 0. Our front pixel now becomes transparent, and we only get the destination. So here they would start off opaque, become transparent at halftime, and then become opaque again as they die, which is not what we want, of course. What we want is this one. So now the other thing to remember is that we've got a lot of overlapping particles, many of them. And this blending is done in a pairwise fashion. Every pair of particles in front of each other is going to blend into a particle that then blends into the one behind it and into the one behind it. So we're going to end up combining a whole bunch of front and back as we move through our pile of particles. And if you recall the colors that we set the red to be some random between 0 and 1, and the green to be some random between 0 and 0.2. So as these things stack up and add their channels together here, both the red and the green, eventually both the red and the green channels will saturate, become 1, as we add up all those numbers that are less than 1. And when they both saturated, red and green combined together make yellow, and we get this bright yellow patch here where many particles have added together with their mostly red but a little bit of green component that is saturated and making the yellow. One other minor point, I don't know if anyone cares. Here's the addition of an on-resize function where I'm going to catch the size from the window's width and height with a little border, set the canvas to be that size and the viewport to be that, and redraw the scene, a minor point. So that's our author's version of particles. I'm going to stop here and next time come back and go through ThreeJs's version of particles. So I'm going to end the share here, back to the full screen. I'm going to stop the recording at this point. I'll come back in with a new recording for the ThreeJs version of particles. So I'll see you all in class. Bye.